position control. So the first one, it's easy enough that you can pull down that little template, right, and build it yourself. You know, the second one with the position control, how are we going to do that? Well, our GP in that case is going to be our theta m over the Vn. Sorry. Okay, and so same thing. Now we have theta m over Vn here. So we want to create a Vn from a controller, right? And we need to, same thing, error, except now the desired theta is the position you want to go to. We're going to now pick up a measurement here and feed that right back. So, sorry. So you could use here the encoder, right? You could even use the tachometer, but that gives you speed and you have to integrate it. You don't want to do that. You want to use the encoder. That's going to give you a direct theta measurement, right? So now, nice thing is that the Quanser Qube, right? That little VI gives you the output from the. It would take a while for you to wire all that up. You know, we don't have a lot of time here. If we had more time on this lab, maybe we'd go through and look at how you build that, but that's why. All right, so you can open up a PD controller that's already built, right? So that's something that we're gonna go ahead and build both a P, you know, plus D, or it's a PD, a proportional derivative controller. And I'm going to try to motivate to show that actually it helps to use both in this case. Okay, so this is the PD controller. I'm going to come back to this, so because I want to show you first. If you want to do first the position control. You know, we want to start off with theta over Vn, which remember is the K that you know, and it's got an S, tau S plus 1. Okay, that's the new plant that we're trying to control. So first, P only. I'm going to have you run some experiments just with P, and you get the closed loop transfer function. You just plug everything. In this case, this is the GP, right? The GC is going to be just the little KP now. Right. When you download this PD controller from Quanser, it's going to have controls for both KP and KD. But first, I want to show you the transfer function for just the proportional. When you do that, and again, I don't have to show all the steps. I think, remember, that's the closed loop transfer function. That's the output of the motor position, and this is the desired, you know, angular position. And when you plug everything in there, remember, you just put everything into the formula again. So it makes these nice linear systems, and the use of linear control analysis and design so nice is you plug in transfer functions here and you can make some nice predictions. When you plug all that in there, I'm going to let you do the algebra. Show that you can get, hold on, it's a little K now. K. I'm just showing the end result because you guys can do the algebra. Divided by, and I'm trying to formulate this to look like a standard second order differential equation. In here you have 1 over tau S plus little kp k over tau, right? If you look at this as a standard second order equation, that's 2 zeta omega n. This is omega n squared, right? By the way, this term right here is also omega n squared, right? So that looks perfectly like a standard second order transfer function. And note that omega n here is influenced only by Kp, right? And here's the important thing about using just P control in this case. Adjusting Kp the only control knob you have with your controller, it doesn't change the damping. And so that's what I want you to kind of observe in lab is, hey, I'm going to just use P control, and I can probably control the steady state error, but this thing's it's going to oscillate too much. You're going to have too much overshoot. It's going to take it too long to settle. It's not when you give it a step input, this thing's going to look like whack, and it's going to oscillate and might take a while. So the value between here, one of the things I'm going to be wanting you to measure in the lab is this overshoot. Sometimes we call that M sub P. In the Ogata chapter, he called it M sub P. How long it might take this thing to settle to within a certain percentage, right, is the settling time. Values like how long does it take it to get to the first peak is also important. So those are the three of the specifications I'm going to want you to play with. Is that all? Let's see. M sub P, T sub P. Yeah, I think that's it. And then T sub S. Then you should measure also the steady state value. To get M sub P is basically, you need to know this value here, let's say the theta steady state, because you need that peak value minus this value gives you the difference, and then you divide by, so like MP is basically theta peak minus theta steady state divided by theta state. That gives you a percentage overshoot, okay? What's really neat is that for a second order system, MP is directly proportional to zeta, right? It's kind of neat. So you're not going to be able to affect overshoot because you can't affect zeta. And that's the key thing I wanted you to see in this, just using P control, okay? And that's why you want to add some D. So I can show you now the G sub C is going to be not only KP, right, a proportional control, and so up here, right, this guy was just KP, okay? I'm now going to make GC, I'm going to add a derivative effect. So I'm going to add another gain, another knob to turn, times S. Because remember, now what you're doing is you're going to say that I want my control, which is in this case, the voltage I send to the motor, I want it to be KP plus KDS times the error, right? So you can see that it's giving you a little proportional part, and it's also giving you a little part that's KDS times E, so it's the derivative of the error, right? The EDT. Okay. So this derivative part is effectively adding this derivative part allows you to have some control. It's anticipating the change in errors, so it ends up giving you a damping effect. Okay, and let's show how that, the way you can see how that is true is you can derive, right, the closed loop transfer function, which is now, again, GC, GP, 1 plus GC, GP, H. When you plug everything in there, I'm going to just show you the end result. Cleaned up. K over little kp plus little kd s all over. It still stays second order, except here you have 1 over tau, 1 plus big K, little kd times s plus little kp, k over tau. Note that omega n squared, that's the same as before. I want you to make note of that. Proportional gain, you can change the natural frequency by itself. That's nice. But note this term now. You remember this is 2 zeta omega n. So you can basically make changes to to zeta for a given omega. In other words, for a given kp, right? Remember, this depends on kp. But you can now change zeta using kd, right? KD influence. You can show, in other words, you can come up with a little formula that says zeta is like 1/2, sorry, omega n. I'm solving this for you, but show that this is the case. So you have a nice little convenient formula. So you see, given this, you can now adjust that and give any zeta you want. And what are some good zetas? Turns out that good zetas are, you know, it's, hey, if I give this thing a step input, and let's say I want it to come to that point, you might not want to overshoot. So maybe you want, you know, critical damping. You know, maybe you use 1.0, or maybe you want some overshoot, but just one overshoot and then it settles. This ends up being a good design value, 0.707. This gives you minimal overshoot with one overshoot, and then also fast rise time, right? So those are two nice design values, and I'm going to ask you to find the KP and KD that give you those values and see how well you could predict that, you know, in the lab. So I'm going to show you this guy so you can see the way they've built their position controller, right? Here's, I'm going to make it red. And I'm just going to ask you to use this guy, and then you've got nice front panel control. Here's the guy that sends the signal to the motor. They're getting the encoder output, and don't worry so much about this little memory thing. What it does is it holds a previous value, and it converts the encoder reading into angle, and then does two things. One is it comes up, follow the signals, it gives you the error signal. That's for your simple P control, and see how it passes into KP. This is this gain. But then it also takes the theta measurement and it sends it into this guy right there. What that guy does is it differentiates it and then also filters it, so in case it has some noise, multiplies it by KD, and then it adds those two there, right, to give you the control, okay? Okay, what else did I want to show you? Yeah, oh, the specifications. I'm asking you to now look at these different responses for second order systems and try to measure some of those in the lab. So I'm gonna, so specifications, the specs, you know, read about those in Ogata, the overshoot, the T sub P, which is time to first peak. And it turns out that TP is equal to pi over omega D, which is pi over what? It's omega n times 1 minus zeta squared. So if you can find zeta and omega n, you can then determine the TP, or backwards, if you find TP, you can estimate one of these guys. So I'm going to propose to you in the lab that, hey, measure the overshoot. It turns out that there's actually a direct relationship between MP and zeta. You can actually find MP given zeta. There's a little formula for it, and I was going to give that to you. Yeah, so don't worry about that chart. But MP is basically, you'll see this in Ogata, but in case you just want to look and listen here, it's 1 e to the minus 1 zeta divided by square root of 1 minus zeta squared times pi. You see that? So if you have this guy, you can find zeta, right? So measure this, get zeta, right? Then now you know zeta, and if you know omega n or you know TP. So here's what you can measure, TP, then you could get omega n. And then you can see how close it is to your model. You can see how, again, how well you can design these systems. So omega MP, TP, settling time, how long does it take to settle? There's a couple there that you might want to read about. I thought I had put them in here, but I didn't. But you'll see it in the Ogata handout. I think I'm going to stop there because I'm going to let you look that up in the Ogata handout. I didn't put notes for myself here. But I have another pre-lab. Okay, so I'm going to just stop there. Sorry. So pre-lab question 4, it says closed loop transfer function, for position control, right? For theta, for 2 different things, P and PD. So I've sort of shown you how to do that. And then it also asks, what's the benefit of adding D? I talked about that, right? It lets you control damping. Oh, and then finally, the last thing is from understanding here, I'm gonna go up here, this transfer function and here, how zeta depends on KP and KD. I wanted to show you, you can do some neat things in terms of showing, hey, how do I adjust KD for a given KP to give me a certain zeta? So I'm gonna stop sharing this screen and jump to my, someone stop this guy. The little MATLAB script. Okay, so all I did in this MATLAB script, and you can download this from the lecture page, is I put in here all the motor parameters, and you guys have your own values that you should use. Then here are the formulas for K and tau. Basically, this summarizes for you even some of the answers for the pre-lab questions. And then here's a P control just for position control. Right? And here's the omega open loop, and then it just gets the open loop response, and then no, this is the closed loop. This is the closed loop response, sorry, for position control, and then here's for PD control, right? And so I'm going to show you what this thing, when you run all of it, it's gonna show you both responses. And then this is the very end. I've plotted KD versus zeta and KP. And so let me run this and go through and study the MATLAB code. It just implements the formulas. So there's 2 things to look at here. First, this is what you should expect to see in the lab. Sorry, there you go. So this plots, the blue one is the P control. That's what you should see when you only have P control. You see how that overshoot is so high, it takes it forever to settle? And here's 0.707 is the orange there, okay? You should see that if you use, and you can test this. This other little chart I wanted you to see is, look, I can, for a range of KP values, I can see what KD value for a given zeta. So like this is zeta of 0.1. If let's say I had a KP of 10, I can go up here and then I can find from the Y there, I can set my KD to 0.36 and it should give me a zeta of 1. If I set, if I want to get 0.707, which is the blue line, I set it at 0.24. So you can see how well the little model graph like this could be used to guide your selection of gains. And that's all. Remember, some of this is to force you to look at the models, derive the closed loop transfer function, learn a little bit about closed loop control, and then see how it works in the lab. And the nice thing about this Quanser Qube is that it really works well in terms of following the model, and everything works nice and linearly and so on. So the last pre-lab question is, create this plot. I've given it to you now. I shouldn't have done that, but I'd rather that you learn how to use it, see a model for how you can create little graphs like this, at least for some of these simpler control systems, and study the effect of different zeta and different KD and learn the different relationships, okay?